I've brought a map tonight, and I want to show you the swindle folded up inside it. Down here along the coast, 1 finger width of paper is a single mile of real ground, an easy stroll before lunch. But up here in the mountains, that same finger width, the very same little gap between my 2 fingers, is 100 miles of hard climbing, a week on your feet. Same paper, same gap. 2 completely different truths about how far apart things really are, and the only thing that decided which truth I got was where on the page I happened to set my hand down.
2 truths from 1 little gap of paper. Go on, I can see there's a question behind it.
So here's what's been gnawing at me since we last sat here. You left me swearing that space-time has a shape, and that the shape is what does all the falling. Lovely. But a map is a worthless scrap until somebody tells me the scale. So where, in all of this, is the little scale bar tucked in the corner, the thing that finally says how much real world 1 step across the paper is actually worth?
You've walked in the door holding the whole evening in your hand, and you don't even know it yet. That little scale bar in the corner of the map, that is exactly the thing I promised you at the top of the stairs last time and refused to name. The something that stores the shape of space-time, point by point. The something that hands every falling apple its marching orders. You asked where it is. It's the scale bar.
That? The dull little thing in the corner is what you climbed the stairs refusing to name?
And here is the fact the whole night lives or dies on. On the map of space-time, that scale bar is not fixed. It changes. Walk a little way across the page and the scale changes under your feet.
Now hold on. A scale bar that changes as you walk, that's not a map, that's a practical joke. The entire point of a scale bar is that it's the one thing on the map you're allowed to trust. 1 inch is 1 mile, top corner, bottom corner, mountains, sea, all the same forever. That's the promise. If the scale goes wandering off while my back is turned, how am I ever meant to measure anything at all?
By asking. Every single step of the way. You stop and you ask the map. Right here, right where your foot is, how much is a step worth just here? And you take your step and you ask again. It is a maddening way to read a map, I grant you. It also happens to be the only honest way to read the real one, the one we actually live inside.
Stop and ask at every step. That's less a map than an interrogation.
And that local scale rule, the answer the map gives back when you stop and ask it at one particular spot, has a name. A plain one, though it wears a rather forbidding coat. It's called the metric.
The metric. And I can already feel you enjoying how bland that word is, sitting there hiding the biggest thing in the room. So say it in words a person can hold. What, plainly, is the metric?
Plainly? The metric is a ruler. That's the honest first word for it. But not one ruler, laid down once and trusted forever. A ruler handed out fresh to every single point in space, so that each little patch of the world carries its very own.
So the measuring stick is never the same twice, place to place?
Stand at one spot, and the metric there tells you what a real distance is, right there. Step across, and there's a new ruler waiting that may not quite agree with the first. It's the universe's way of answering, at every place you could possibly stand, the one question a map can't dodge. A step from here to there, how far is that, really?
So it's less a scale bar in the corner and more a scale bar painted onto every square inch of the map, and no 2 of them quite promising the same thing.
That's it exactly. And I want you to hear how badly that breaks the arithmetic you were raised on. Cast your mind back to the schoolroom, the oldest rule for distance there is. You want to know how far across a field it is, cutting straight from corner to corner. You pace out the one side, you pace out the other, and there's a tidy little recipe that turns those 2 into the diagonal, the straight line across.
I know the one. Square this side, square that side, add them up, and the diagonal falls out. I had that hammered into me before I was 10. It's about as solid as arithmetic gets. It's practically what distance means.
It is what distance means, on a flat sheet of paper. That recipe is the ruler of the flat page, written out in full. And here's the quiet bombshell. On the true map of the world we're sitting in, that recipe is not the same in every field. Cut across a field down by the coast, and the old recipe holds perfectly. Cut across a field up in the warped country near a heavy mass, and the recipe has changed. The squaring, the adding, the very rule that turns 2 paces into a diagonal has been altered because the ruler there has been altered.
So the right-angle recipe itself gets rewritten, field by field, depending on where I happen to be standing. That's genuinely upsetting. That's the sort of thing that keeps a person up at night.
It kept a great many people up a great many nights, and one of them got a whole new theory of gravity out of it, so the sleeplessness wasn't wasted. But yes, that is the metric, said in its bones. It's the local recipe for distance, the measuring rule of this particular patch, allowed to be different from the patch next door. And now gather up all those little local recipes, one for every point there is, into a single object. And that single object is the shape of space-time. It doesn't describe the shape, it is the shape. There's nothing left over.
Slow right down, because you slid a whole planet past me in that last breath. You're telling me that if I knew the ruler at every point, every one of those local recipes everywhere at once, I would know the entire shape of the thing. Not a picture of it, the thing itself. There's no separate shape sitting behind the rulers that the rulers are only reporting on.
There is not. And that's the part people find hardest to swallow, so I'll say it as bluntly as I know how. You keep wanting the shape to be a thing, and the ruler to be a report about the thing. As though the mountain is really up there, and the map is only gossip about the mountain.
But surely the mountain is still there whether or not I map it.
But inside the world, we never once get to climb out and look at the mountain. And when you're always only inside, there is no separate mountain to check the map against. All you can ever do is lay down rulers and read them. The complete set of rulers is the complete truth.
This is your ant, isn't it? From last time. The little ant crawling about on its surface, that could prove its whole world was curved without ever once leaving it. No outside to peer in from, no balcony, just the ant and its little instrument.
It's precisely my ant, and I'm delighted you kept hold of it. Remember what the ant had to work with. It couldn't float up above its world and see the bulge. All it had was a tiny ruler and the patience to crawl about, laying it down over here, over there, measuring little distances and little triangles.
And from those scraps alone the ant could know, without ever seeing the bulge.
And out of nothing but those local measurements, nothing but the ruler, used again and again, the ant could tell, for certain, whether its world was flat or curved. Well, the ruler the ant was crawling around with, that is the metric. The metric is the ant's ruler, promoted to a law of physics and painted onto every point of space-time at once.
So the metric is how the inside of a world talks about its own shape. It's the shape described from within by somebody who can never get out.
The shape described from within by somebody who can never get out. Write that on the wall. Most of the trouble people have with curved space-time comes from secretly wishing they could get out, wishing for the God's eye look down at the bent sheet. There's no such view. There's only the ruler and the crawling and the reading off. And the astonishing thing is that it's enough. The ruler alone tells you everything there is.
All right, I'm holding the ruler at every point, but you've been letting me say distance this whole time, as though it only ever measures across the ground, and I've a nagging memory that the last 2 courses kept insisting the one word I'm never allowed to leave out is time. That space on its own is only ever half the story. So don't tell me this ruler only measures across a field.
No, and you've put your finger on the thing that turns a nice bit of geometry into the reason apples fall. The metric is not only a ruler, it's a ruler and a clock welded into one. Ask it about a step across the ground, and it answers with a real distance. But ask it about a step forward in time, a tick, and it answers just as readily with a real duration. How much genuine lived time is one tick worth, right here at this spot? And that answer, exactly like the distance answer, is allowed to be different from place to place.
Oh, I don't like where that's going, and I like it enormously, both at once. You're saying the same object that tells me a step across the field might secretly be a mile, or secretly 100 miles, also tells me a tick of the clock might secretly be worth more time here than it's worth over there.
The very same object, one ruler for space, one clock for time, bound so tightly they aren't really two things. They're the one thing, the metric, answering two flavors of the same question. And near a heavy mass, both of its numbers drift as you move. Now feel the old ghost walk back into the room. Because a clock whose tick is worth more time in one place than another, we have met that clock before.
We built it, 2 courses back, out of nothing but a rocket and our own 2 hands. The clock at the top of the accelerating rocket ran faster than the clock down at the floor. And then you did the wicked thing. You told me that by the equivalence, gravity and acceleration being the same to anyone shut in a box, the same had to be true in plain gravity. A clock up high runs faster than a clock down low, time itself running at different rates at different heights. I didn't sleep after that one either. You've a real habit of this.
I do keep you up. But look what's happened tonight. Back then, that mismatched clock arrived as a shock, a rabbit pulled from the equivalence hat. Tonight it arrives as a line in a ledger. When I say the clock part of the metric is different at the top of the tower than at the bottom, I'm saying, in the flattest bookkeeping language there is, the exact thing that so unsettled you before. Clocks run at different rates at different heights. Only now it isn't a rabbit, it's just the clock part of the ruler reading a slightly different number upstairs than down.
So the eerie thing from the rocket, clocks disagreeing by height, you're now telling me is just an entry in the scale bar. It was the scale bar changing the whole time, and I hadn't the word for it.
You hadn't the word for it. Now you do. Gravitational time dilation is nothing more and nothing less than the clock part of the metric changing from place to place. Time dilation and the metric are the same fact, wearing different clothes. And hold on to that one, because in about half an hour it's going to reach up and explain why you're sitting in that chair instead of drifting off the ceiling.
I mean to come back and collect on that threat. But first, you've now told me twice the metric differs from spot to spot near a mass, which forces the obvious question, what does it look like when it's the same everywhere? When the ruler doesn't change, and the clock doesn't change, and the right-angle recipe behaves itself in every field from here to the horizon.
Now that's the right question, and the answer's a name you already own. When the metric is the same at every point, one ruler, one clock, laid down identically across all of space and all of time, never drifting, never leaning, that is flat space-time. And flat space-time is nothing on this Earth but the world of the last season. The steady, rigid, everywhere identical stage of special relativity. The elastic universe that turned out not to be elastic at all.
So the entire previous course, the one speed of light, the whole business, that's just the special case where the ruler never changes.
That's the whole of it. That's why they called it special. When the metric is flat and unchanging, there is no gravity anywhere. None. Clocks that all agree about the rate of time, rulers that all agree about distance, light running dead straight, the whole tidy machinery you spent 8 nights learning to love. A beautiful map. A true map. of a world with no gravity in it.
And so gravity, then.
And so gravity, then, is the metric that is not that. Gravity is the ruler that changes as you walk. Gravity is the clock that leans. Gravity is the scale bar you cannot trust from corner to corner, because near a heavy thing it drifts, and the tick of a clock is worth a hair more up here than it is down there.
Every one of those is just the ruler refusing to hold still.
That is the entire content of the word. Gravity is the local difference between this metric and the flat one. Wherever the ruler departs from the honest, everywhere identical ruler of the last course, that departure, and nothing else, is what we've been calling gravity for 300 years.
Let me sit in that, because it's the kind of sentence that sounds simple and then detonates a second later. For 300 years, we said gravity is a force, a pull, something the Earth does to the apple, reaching out and yanking it down. And you've just quietly swapped the whole picture out from under me. There's no reaching, there's no yanking. There's a ruler near the Earth that isn't quite the same as the ruler far from it. And we've been calling the difference a force the entire time.
The entire time. And I want to be fair to the old picture, because it isn't wrong so much as it's a brilliant disguise. The force of gravity that Newton wrote down works magnificently. It lands ships on other worlds. It's beautiful. It's very nearly right. But it's a description of the symptom. It's what you see if you never think to check whether your rulers agree.
So Newton described what falling looks like, and Einstein asked what it actually is.
Einstein's move, the whole move, the one that took him 10 years and nearly his sanity, was to stop describing the symptom and go after the cause. And the cause is that the map's scale is bent. Everything Newton called force, Einstein called geometry. Same falling apple. One man says a force pulled it, the other says the ruler leaned, and the apple simply went straight.
The apple went straight. That's the bit I have to keep relearning, because it fights every instinct I've got. Last time you made me swallow that a falling thing isn't pushed or pulled at all. It's going as straight as anything can go, along the straightest possible path through the shape. The geodesic, the orbit as a straight line. The great circle on the globe that only looks bent because the world underneath it is round.
You've kept every piece of last time. Good. But I can feel a but coming.
But I still don't see how the ruler actually reaches out and steers the apple. Knowing the local scale of a map tells me how far things are. How on earth does it tell the apple which way to go?
Now we arrive at the piece that made me fall in love with this whole subject, because it's so much better than it has any right to be. You've drawn a line between two things you think are separate. Over here, the ruler, the thing that measures. Over there, the steering, the thing that decides which way the apple falls. And you're assuming there must be some extra machinery bolted between them, an engine that reads the ruler and then does the pushing. There isn't. There's no extra machinery. The steering comes straight out of the ruler, for free, with nothing added at all.
No, that can't be free. Measuring and steering are just plainly two different jobs. One's a tape measure, the other's a steering wheel. You don't get the wheel thrown in with the tape.
You do, and here's why. And it's the loveliest little argument in the whole theory. What is the straightest path? Not on flat paper, you know that one. What is the straightest possible path across a shape whose ruler changes from place to place? Think about what straight even means to somebody trapped inside. It can't mean matches a straight line drawn from outside. There is no outside.
Then what's left to mean straight if you can never step outside to draw it?
So it has to mean something the ant could check with its own little ruler. And here it is. The straightest path is the one that, step after step after step, doesn't waste any length. The shortest way. The path that, measured by the local rulers all along it, comes out to the least total distance between where you started and where you're going.
The shortest path. measured with the local rulers, like a string pulled tight. On the globe last time, the tightest string between two cities lies along a great circle, and the great circle is the straightest path a thing can take on a sphere. Looks bent on the flat map. It's the straight one, really.
The string pulled tight. Hold that image, it's perfect. Now watch what it means. To find the tightest string, the shortest path, you have to compare lengths. This route, that route, which comes out shorter. And to compare any lengths at all, you need the ruler, the metric. So the moment I hand you the ruler at every point, you can find the tightest string between any two events all on your own.
So the rulers alone hand me the tightest string. All right, then what?
And the tightest string is the straightest path, and the straightest path is the one the free apple takes. The ruler doesn't just measure the path after the fact, the ruler picks the path. Steering and measuring were never two jobs. They were one job you were looking at from two sides.
Oh, that's clean. That's properly clean. The metric measures distances, and because the straightest path is only the shortest path, the very same metric that measures the distances also chooses the path. The tape measure was the steering wheel all along. I only thought they were different because I'd never noticed that straight and shortest are the same word wearing two hats.
The same word, two hats. And that, at last, is the promise I made you at the door last time, paid in full. Something has to store the shape of space-time, I said, and hand each falling thing its marching orders. Well, the metric stores the shape. It is the ruler at every point.
The shape stored. That's half the promise. And the marching orders?
And the marching orders fall straight out of it, because the orders are nothing but, take the tightest string, and you need the ruler to know which string is tightest. One object. It holds the geometry, and it issues the commands, and there's not a scrap of anything else required. Give a universe its metric, and you've told every apple, every planet, every beam of light exactly how to move. Forever.
That's a stupendous amount of work for one object to be doing. It's the map, and the itinerary, and the driver, all at once. Right, now I'm going to be a nuisance because there's a picture in my head that everybody gets shown, and I want to know if it's the truth or a lie. The bowling ball on the trampoline.
Go on. Lay the whole toy out for me before I break it.
You put a heavy ball in the middle of a stretched rubber sheet, it makes a dip. You roll a little marble past it, and the marble curves into the dip and round like a planet. Every single person who's ever tried to explain gravity to me has reached for that sheet. Is it right?
The rubber sheet. I knew it was coming. They always bring the sheet. Let me answer you honestly, because the honest answer is more interesting than a simple yes or no. The sheet is a lie. A useful lie, one that got a great many people through the door. But a lie in two separate ways at once, and once you see both of them, you can never quite look at the sheet the same way again.
Two ways. All right, break my childhood toy. Gently. What's the first lie?
The first lie is that the sheet is a cheat. It explains gravity by quietly using gravity. Ask yourself, why does the marble roll down into the dip? Why does the bowling ball make a dip in the first place? Because they're heavy. Because real gravity, the actual downward pull of the actual Earth, under the table the whole demonstration is sitting on, is dragging them into the rubber. Take the sheet up into deep space, away from all gravity, lay your bowling ball on it and… nothing. No dip. The ball just floats there.
That's marvellous. That's a proper swindle. The trampoline can only show me how gravity works by keeping a whole Earth hidden under the floorboards, secretly supplying the actual pull. It's a magician who does the vanishing coin trick by keeping a second coin up his sleeve.
A second coin up the sleeve, exactly. It's a picture of gravity that runs on gravity. It explains the fire by pointing at a fire. That one's almost forgivable, a demonstration needing a floor to stand on. But the second lie is the one that actually matters, because it hides the deepest and most beautiful thing in this whole course.
Then don't keep me waiting. What is the second lie?
The sheet shows you space being bent. A flat rubber sheet dented downward. That's a picture of space, curved. And it leaves you dead certain that gravity is space warped into a valley, with things rolling down the sides. But near the Earth, near anything you or I will ever fall toward, it is almost not about the bending of space at all.
Not space. Then what's doing it?
The thing doing the falling, the thing that holds you in that chair, is not mainly the bending of space, it's the bending of time.
The bending of time. Say that again, slower, because I felt the floor move a little.
The bending of time, not space, or rather, not mainly space. Let me lay it out with all the care it deserves, because this is the summit of the whole evening, and if you take one thing home tonight, it should be this one. We agreed the metric is a ruler and a clock together, a scale for space, a scale for time, and near a mass both of them drift from place to place.
A scale for space and one for time, neither of them fixed. Give me the fact you promised.
Here's the fact that took my breath away the first time anyone laid it out for me properly. Near the Earth, in the ordinary, gentle, everyday gravity you and I stand in, the drift is lopsided. The space part of the ruler barely changes at all. The distances around you are very nearly the honest flat ones.
So space barely feels it at all. Then what's doing the pulling?
But the clock part, the rate at which time itself ticks as you go up and down, that changes enormously by comparison. That's where nearly all the gravity is hiding, in the leaning of time, not the bending of space.
Now wait. That is completely backwards from everything I thought I knew. I've spent this whole course, 2 courses, being told the great revelation is that space gets curved. Curved space-time, the bent sheet, the ant on its bulging ball. And now, at the top of the mountain, you turn round and tell me the thing actually pinning me to the ground is barely about space at all. It's about clocks running at different rates. That feels like a betrayal.
It feels like a betrayal, and it's the payoff of the entire season, so let me earn it. You want to know why the apple falls? Truly why? Not, a force pulls it. We've thrown that away, but the real geometric why. Cast your mind back, one more time, to that clock. Time runs a touch faster high up, a touch slower down low, nearer the Earth. The clock part of the metric leans. Up is fast, down is slow.
So the clock tilts like a hillside near the Earth. And a falling thing does what with a tilt like that?
Now, a freely falling thing does not seek out any particular place. It does one thing, and one thing only. It follows the straightest path. And the straightest path, for a thing moving through time, turns out to be the path that racks up the most time on its own clock. The path that ages the most.
The path that ages the most. That's a strange and rather wonderful thing to say. The apple is greedy for time. Given every possible route through its little slice of existence, it takes the one that lets it live the most seconds.
Greedy for time. That's the spirit of it exactly, and it's the deepest law of motion there is. Now watch it bite. Toss a ball straight up and let it fall back to your hand. Why that arc? Why does it rise, slow, stop, and fall in that particular curve, and not some other? Because the ball is hunting for the most aging it can get between leaving your hand and returning to it.
So the arc is a hunt for the most lived seconds. What's the catch in it?
And it faces a bargain with 2 sides. On the one hand, up high the clocks run faster, so climbing wins it extra aging, more lived time, just for being up where time runs quick. That tempts it upward.
And the other side of the bargain,
To climb at all, it has to move, and moving, going fast, slows your clock. That's the old lesson from the last course. Motion costs you time. So racing up too eagerly spends aging even as the height earns it. And the actual arc the ball traces, the rise, the hang, the fall, is nothing but the perfect treaty between those two. Climb just high enough that the faster clocks up top exactly pay for the time lost in the moving. Not a hair higher, not a hair lower. That treaty, drawn out through time, is the arc. That is the falling.
So the shape of a thrown ball's flight, that homely little curve I've watched 10,000 times, is a negotiation. It's the ball finding the sweet spot between get up high where time runs fast and but don't move so hard you spoil it. And the answer to that negotiation just is the path we call falling.
Just is. And now feel where all the weight in that argument sits. Every bit of the pull, every bit of the temptation to climb came from the clocks, from time running faster up high and slower down low. The leaning of time.
So the clocks do all the pulling, and space just sits this one out.
The bending of space never once entered the bargain, because you and I and the apple move so laughably slowly through space compared with how fast we all rush through time. We're practically standing still in space and hurtling through time at the only speed there is.
Racing through time flat out, crawling through space. So what does a small tilt do to a motion that huge?
And when you're barreling through time that fast, even the faintest lean in the rate of time, the tiniest tilt in the clock part of the metric, grabs your enormous motion through time and bends a sliver of it downward into motion through space, into falling.
So that's what you meant half an hour ago when you threatened the eerie clock would reach up and explain why I'm in this chair. It's the whole thing. The clocks at my head running a sliver faster than the clocks at my feet. That isn't a curiosity. That sliver is the gravity. That leaning of time is precisely why I don't float off the ceiling. I'm being held down by the fact that time runs slower at my feet.
You are being held to that chair by the slope of time. Let that sit. The floor doesn't push up on you because of some force in the rock. You press down on the floor because your natural, free, greedy for time path, the one you'd take in an instant if the chair vanished, leans down the slope of time toward where the clocks run slow, toward the center of the earth.
So I'm forever trying to fall toward the slow clocks, and something's in the way.
The chair is the only thing stopping you from taking it. The falling you feel every second of your life, the falling you never think about, is you leaning against the grain of time and the chair holding you back.
That is the single strangest true thing you've ever told me, and you've told me some contenders. Let me try to say it back so I know it's really in me. A falling apple isn't being pulled down, it's following the grain of the metric, sliding along the lean of the clock part, down toward where time runs slowest. Because that's the path that ages it the most, and aging the most is the only thing a free thing ever does. Falling is just going with the grain of time.
Falling is going with the grain of time. You've got it whole. And notice what you did not say, which is anything about a force. There's no force in that sentence anywhere. There's a ruler and clock that leans near the earth, and a thing going straight through it, and the going straight, read out in ordinary words, is the falling of the apple. One object, the metric, has swallowed the entire force of gravity and left nothing behind but geometry. That's the beauty I promised you at the start. Not gravity explained, gravity dissolved into the shape of a ruler.
But now I have to press you because you were very careful a moment ago and I noticed. You kept saying, near the Earth, everyday gravity, the space part barely changes. You were building yourself a little escape hatch. So tell me straight, are you actually saying space isn't curved at all? That the whole curved space business was a fairy tale? and it's really all just clocks?
No, and I'm glad you caught the hedging, because this is a place people fall straight off the path in the other direction, and I won't let you. Space is curved. Genuinely, really, measurably curved. The ant near a heavy mass would lay down its little triangles and find the angles don't add up right, the same as on the bulging ball. That is not a fairy tale. It is true, and near something truly monstrous, it becomes enormous.
So space really is curved. You're not taking that back. Then what's the fine print?
What I'm telling you is narrower and more delicate. In the weak, gentle, everyday gravity we live in, the Earth's mild pull, the sort that shapes a thrown ball, the bending of space is real but tiny, and the leaning of time does almost all the work of falling.
Both present, then, just tilted hopelessly toward the clocks. I can hold that.
Both are there. They're just wildly out of balance in our little corner. It's not that space is flat, it's that time outbends space by a landslide, whenever the gravity is weak and the falling things are slow.
When the falling things are slow. There's another hedge. You've said it twice now. So what happens when the falling thing isn't slow? When something comes tearing through at a real clip?
Then it starts to feel the bending of space too, because a thing moving fast through space samples the space part of the ruler the way we, dawdling along, never do. Send something through at a truly ferocious speed, and the curvature of space stops being a footnote and starts to add its own share to the bending of the path.
Fast movers taste the curve of space. Is there something that always moves that fast?
And there is one traveller in the universe that goes at the most ferocious speed there is, always, with no choice in the matter. And when that traveller skims past a heavy mass, the bending of space is no longer a footnote.
Light. You mean light. Say the rest.
But that's a door I'm going to leave shut tonight. What's behind it is one of the three great triumphs of this whole theory, and it deserves a night of its own. For now, hold only this. Slow things fall by the leaning of time. Fast things start to feel the bending of space as well.
You dangle these doors in front of me and then slam them, you know that? Fine, it's shut. I'll come back for it. But let me make sure I've truly got the main thing, the thing you called the summit. Near the Earth, the metric barely bends in its space part, but leans a good deal in its time part. Falling is going with that lean of time. And the reason nobody ever told me, the reason everybody shows me the bent rubber sheet all about space, is that the sheet is showing me the tiny part and hiding the whole part.
That's the indictment, and it's a fair one. The sheet draws the little bit of space curvature, which you can see, as a dip in a surface, and it says nothing at all about the leaning of time, which you cannot draw as a dip in anything, and which is doing nearly all the falling. So the picture everyone learns first is a picture of the least important part of gravity, dressed up as the whole of it. That's why I'd rather you carried the map with the changing scale bar and the greedy for time apple than the trampoline. They're harder. They're also true.
The map and the greedy apple. All right, I'll trade the trampoline in, though I'll miss rolling the little marbles. Now, you've done something over this last hour that I want to name out loud, because I don't think you've owned up to how big it is. You started the night with a force, gravity, the thing that pulls, and you've ended it with no force at all.
Go on. Name what I did, plainly. I want to hear you say it.
You've replaced the entire idea of a pulling force with one geometric object, this ruler and clock, this metric, that leans near a mass and steers everything and ages the apple and holds me in my chair. The force is just gone, retired. You put a whole fundamental force of nature out to pasture and replaced it with a bent tape measure.
I did, and when you say it that plainly, it still gives me a chill after all these years. That is exactly what Einstein did. He looked at the oldest, most obvious force there is, the one that's been falling apples on people's heads since the beginning. And he said, "It isn't a force, it's the shape of a ruler."
He just retired the oldest force there is. And nothing's lost?
Everything you attributed to a pull, I can get from geometry, from the lean of time and the faint curve of space, with no pull anywhere. And the object that does it isn't even exotic. It's a ruler and a clock, the two humblest instruments there are, just allowed, for the first time in the history of the world, to change their minds from place to place.
A ruler and a clock allowed to change their minds. I'll carry that up the stairs. But, and you knew there'd be a but, you can see it coming a mile off, you have very quietly left a colossal hole in the middle of tonight, and I'd be a poor student if I let you walk out without pointing at it.
Out with the hole, then. I'd expect nothing less from you.
You've told me, top to bottom, what the metric does. It stores the shape, steers the apples, leans time, dissolves the force. Beautiful. But you have not breathed one word about where the lean comes from in the first place. Why is the ruler bent near the earth and flat out in empty space? Something must be doing the bending. The metric can't just decide on its own to lean near a planet and lie flat far from one.
No, it cannot. And you've walked us, dead on time, to the edge of everything. I've handed you a magnificent machine and told you nothing about what winds it up. All night I've been describing a geometry that leans near a mass, and I never once told you why the mass gets a say. Why should a lump of rock and iron out there have the faintest thing to do with how a ruler behaves or how a clock ticks in the empty space around it? What is the mass whispering to the geometry to make it bend?
And I can hear from the drop in your voice that you already know the answer, and that it's another one of your trapdoors. So let me guess at the shape of it, at least. We've had half of a conversation tonight. Geometry tells matter how to move. The ruler steers the apple. The metric hands out the marching orders. The falling is going with the grain. That's the half we did. And the missing half, the hole I'm pointing at, has to be the other direction. Not geometry telling matter how to move, matter telling geometry how to bend.
Matter telling geometry how to bend. There it is. You found the second half of the sentence with your own two hands. All night, one direction only. The shape tells the apple where to go, and running back the other way, the direction we haven't touched. The rock, the star, the stuff tells the shape how to lean. Two arrows pointing opposite ways, locked together. Matter tells space-time how to curve. Curved space-time tells matter how to move. Each one feeding the other, round and round forever. Each defining the other in the very same breath.
And that two-way street, matter bending geometry, geometry steering matter hand in hand, that's got to be written down somewhere. That's got to be an actual law. The rule that says how much a given lump of stuff leans the ruler around it.
It is a law. It is one law. And it is the thing this entire course has been walking toward from the very first night. The most famous equation you have never once been shown. You've heard the name of it. You've seen it invoked to mean impossibly clever. But I'd wager you've never been told what it actually says.
The name, yes, and not one word of the meaning. So tell me the meaning.
And what it says is precisely the handshake you just described, made exact. It has two sides. On the one side, the shape, the bending of the ruler, the lean of the clock, everything we've built tonight. On the other side, the stuff, the matter, the energy, all the somethings that fill the world. And an equal sign between them, saying they are, forever, the same thing seen from two directions.
The shape on one hand, the stuff on the other, and an equal sign holding them together like two hands clasped. And I take it you're not going to show me that equation tonight either.
Not tonight. Tonight was the metric, the geometry, the ruler that leans, the apple greedy for time. You've earned the whole of the geometry tells matter how to move half, fair and square, and that's a full evening's work and then some. But come back down the stairs next time and we'll take the other half, the one where matter reaches out and tells the shape of the universe how to bend.
The other half of the sentence, at last, I'll come running, though I feel a catch coming.
And I'll warn you now, the way I always do, because it's only sporting. That equation, the two-sided one, the moment somebody solved it, really solved it, for the space around a single heavy ball, something came crawling out of the answer that even Einstein himself didn't believe was real. Something with an edge you could fall through and never ever climb back out of.
You're doing it again. You're leaving the light on in a room I can't go into yet. All right, I'll come. Let me carry the right things up the stairs with me, so I've got them ready. No force, that's the first one. I'm putting the pull down at the bottom of the steps and not picking it back up.
Good. That's the first and best thing to set down. Now, in its place,
Instead, a ruler and a clock, welded into one thing and handed out to every point there is, the metric, and near a heavy mass it leans. Where it never leans, that's the flat world of the last course, and there's no gravity in it at all. Where it does lean, that leaning is the gravity, all of it.
just so. And one piece still missing. How does a mere ruler drive anything?
And the steering comes free because the straightest path is only the shortest path, and you need the ruler to know which path is shortest. So the same object that measures the world also drives everything through it.
Every word of it true. Go on. You've one more thing to carry, and it's the heaviest.
The heaviest thing, yes, that when I fall, when anything near the Earth falls, it's mostly not about space bending at all, it's about time. Time runs a sliver slower down at my feet than up at my head, and a falling thing is only ever doing one greedy little thing, taking the path that lets it live the most time.
That's the entire law of a free thing. Nothing but that. Keep going.
And going with that grain, sliding down the slope of the clocks toward where they run slow, is the whole of what falling is. I'm held in this chair by the lean of time. That's the one I'll have the hardest time believing when I wake tomorrow, and it's the one you said was the summit, so it's the one I'll hold tightest.
Hold it tightest. It's the truest, strange thing the two of us made all night. And it's the payoff of everything we did 2 courses back, with that rocket and its mismatched clocks. The clock at the top of the tower running fast, that wasn't a party trick. That was gravity showing you its real face, a whole course before you had the word for it. Tonight you got the word, the metric, the ruler that leans. And the leaning of time is the falling of the world.
The leaning of time is the falling of the world. I'll walk up the stairs saying that one under my breath, and I'll be down early next time, because you've got me now. You've shown me the shape, and told me the shape tells everything how to move, and then left the biggest question of the lot sitting in the middle of the floor, glowing. What tells the shape how to bend? What does a lump of matter whisper to the empty space around it to make the very rulers lean and the very clocks slow?
That's the whole of next time. Carry the question up with you.
You said it's one law with 2 sides, and a solution so strange even the man who wrote it flinched from it. So don't oversleep, because I mean to find out what the universe is saying to itself in that equation, and I've a feeling that once I hear it, I'll never look at a falling apple, or a heavy star, or the empty space between them the same way I did tonight. Good night,